Hello, let us continue our study of reduction, polynomial time reduction between problems. And then I will define a very important subclass of problems in the complexity class NP. So, reduction continued. Okay, so one thing let me start with. If there is a polynomial time reduction from some problem pi 1 to some problem pi 2, and if I have another reduction from the second problem to the first problem, then we say these two problems are equivalent, polynomial time equivalent, and often we write it as pi 1 and pi 2 are equivalent. So far we have proved that the Ham cycle problem reduces to the Ham path problem and also conversely. Hamiltonian cycle and Hamiltonian path problem. So this shows that they are equivalent. Using very similar constructions, we can show that the same problems, the Hamiltonian cycle and the Hamiltonian path problems for directed graphs are again equivalent. Okay. Today I will propose, or I will start with the proposal of the equivalence of this. This construction automatically, in a very similar way, also proves the equivalence of this and this, but this is also not necessary because this is equivalent to this, this is equivalent to this, this is equivalent to this. So by this wrong route, these are already equivalent, but anyway, the construction that I will propose for this will work even for proving this equivalence. So I will start with this reducing to this. That is, so that Ham cycle this is a question about undirected graphs, reduces to the same question about directed graphs. So the idea is, given an undirected graph G, I want to construct a directed graph G prime such that G as an undirected Hamiltonian cycle if and only if G prime has a directed Hamiltonian cycle. Okay, the construction turns out to be very similar, very easy. So, the vertex set of G prime is taken as the same as the vertex set of G. Okay. Moreover, for each undirected edge u comma v in E, add two directed edges u comma v and v comma u to the edge set E prime of G. That's all. That's all about the construction. And you see that this works. With this simple-minded construction, this property, this requirement is satisfied. I am leaving it to you because it's almost obvious. Okay. At least almost obvious to me. So, one direction, done. What about the other direction? This is little bit trickier. So, detected Hamiltonian cycle reduces in polynomial time to the undetected Hamiltonian cycle problem. So, somehow I have to capture the notion of direction in an undirected graph. Okay, so once again this is same. Given a directed graph G, I need to construct an undirected graph G prime such that G has a directed Hamiltonian cycle if and only if G prime has an undetected Hamiltonian cycle. So, how to proceed? Okay. Somehow, the sense of direction in G has to be transported to G prime. So, now take any vertex u in the vertex set of G. Okay. Split it into three vertices. U in, U out. Okay. So I have some U here. In the target graph, G prime, I will have three vertices, U in, U and U out. And I will give connection like this. This. Okay. Now, if there is, okay, so these are undirected connections. Now, if there is an incoming edge to U, so this V will also be split into three parts, V in, V out and V itself. So, I will give this connection. For each such connection, I will give V out to U in. So, outgoing edge, incoming edge. Likewise, if I have a vertex W and I have an outgoing edge here, so there will be some W in somewhere. So, sorry. Small mistake. This should not be a directed edge. This is an undirected edge. Okay, this is an undirected edge. Sorry. So this will be an undirected edge. Okay, so likewise, if I have an outgoing edge from you, outgoing to incoming node for W. So, this is the way I introduce the sense of or port the sense of direction from a directed graph to an undirected graph. So, there are two questions. First, I have to show that this construction works. G has a directed Hamiltonian cycle if and only G prime has an undirected Hamiltonian cycle. So, I leave it as an exercise to you. 1. Correctness of the construction. And there is a second thing. You may actually find it rather unintuitive or counterintuitive. What is this U doing here? Can I not simply split U in and U out and do these connections like this? So, this is once again a second exercise. So, exercises show that construction does not work if U is not there. Okay, so these are simple things, but I leave it to you. Okay, with this the construction will work, but if you just connect U in and U out without having U acting as a bridge between U in and U out, this construction will not work. Okay. Anyway, so therefore this Hamiltonian cycle or Hamiltonian path problems are equivalent to one another, and it does not matter whether we are talking about directed graphs or undirected graphs. Fine. So we have seen several examples of reduction. Now I define the most important concept in this chapter. Definition. A problem pi is called, let me write it in another ink, NP hard if there is a polynomial time reduction from every problem pi prime in NP to pi. Okay. So this essentially means that whenever I have any problem pi prime in NP, I have a reduction like this. Okay. So this essentially means that the problem pi is so hard, so difficult, that if that can be solved easily, then all problems in NP can be solved easily. Right. So reduction essentially means this. Reduction followed by running an algorithm of the target problem gives you a way of solving the source problem. But that need not be the only way of solving the source problem, or even the best way of solving this source problem. This is just one way. It can be solved perhaps by easier algorithms, less complicated or less complex algorithms. So this is less than equal to is because of that. Now this says a problem pi is so difficult that if I can solve this problem easily, then all the problems in pi prime in NP, all problems pi prime in NP can also be solved easily, efficiently in polynomial time, for example. Okay, but this NP hard actually does not capture the very correct notion, so I give a second definition, which is the most a problem most relevant in this context. Pi is called, once again choose another color, NP-complete if following two holds. One, the problem pi is itself in NP. Two, pi is NP hard. Okay. So, NP hard problems may remain outside the complexity class NP itself. In the end, I will give you an example that in order to be NP hard, a problem need not stay in the complexity class NP. So, if this condition is necessary. Okay, I will give you an example at the end of this section. Not today, a few days later. So, this is not automatic. Okay, condition 1 is not automatic. Keep it in mind. So, I have identified some problem in the class itself which is at least as difficult as all other problems of NP. Okay. So, rightfully, therefore, NP-complete problems can be thought of as the most difficult problems in the complexity class NP. Okay. So, an NP-complete problem, loosely speaking, is one of the most difficult problems in the complexity class NP. Okay, so this is just an intuitive understanding, but what I say next gives the NP-complete problems their importance in the study of the P equal to NP problem. If any NP-complete problem can be solved in polynomial time, then P is equal to NP. Conversely, if some NP-complete problem can be proved to be unsolvable in polynomial time, then P is not equal to. Okay, so why? First statement, let's say. Second one is actually almost obvious. So, we already know P is contained in NP. So, I want to prove the converse in order to prove this equality. So, take any problem pi in NP. Okay. And it is given that, or maybe I say, maybe I'll proceed this way. Okay. Let pi in NP be NP complete, and let A be a polytype algo for pi. Okay. Then I take any pi prime in NP. So from pi prime to pi, I have a polytime reduction R. Okay. Okay. By definition of NP-completeness, and this can be solved by that algorithm A. So R followed by A is a polynomial time algorithm for solving pi prime. Okay. Why? Because this runs in polynomial time, it cannot produce an output instance which is super polynomial in size in this input. Okay, it has to be a polynomial, and that polynomial runs, that polynomial sized input is handled by this A, which runs in polynomial time. Okay, so R followed by A, this is the recipe for polytime algo, polytime recipe for solving pi prime. So pi prime is in P. Therefore, since pi prime was arbitrarily chosen, NP is a subset of P. P is anyway a subset of NP, so they are equal. And for the second statement, this is pretty obvious. If there is some NP-complete problem that cannot be solved in polynomial time, by definition, that problem belongs to the NP class NP, and you clearly have NP not contained in P, because there is at least one member of NP which cannot be solved in polynomial time. So NP cannot be equal to P. So this is more or less trivial or obvious. Fine. So this is why NP-complete problems play a very important role in the study of the P equal to NP question. Okay. So of course, this definition is good, and you understand the importance of NP-completeness. So, are there NP-complete problems? This is the obvious next question. And the big answer is yes. There are thousands of known NP-complete problems. Okay, so but then next question is how to prove NP-completeness. Okay, this definition says that, okay, proving some problem to be in NP is just showing some certificate or providing some sort of non-deterministic polynomial time algorithm. This part is easy. But for proving this hardness, I have to pick any problem pi prime in NP and show that that problem reduces in polynomial time to pi. But the complexity class P itself is already infinite. NP is a superset, possibly strict superset, but anyway it's a superset. This also contains infinitely many problems. So how can I supply a proof for each of these infinitely many problems to the specific problems pi? Okay, apparently seems very difficult. So this involves actually not a problem by problem, case by case basis reduction, but a generic reduction. Okay. And then we have problem to problem reduction. Okay. So this generic reduction is a very difficult thing. In fact, it can best be proved if you adopt the notion of non-deterministic Turing machines which run in polynomial time. Okay, so a generic reduction, it's good if you use non-deterministic Turing machines, polytime, and assume that it has some kind of transition function, work on that transition function, and this makes problem somewhat simpler. Instead of talking about C programs or your pseudocodes, okay. And this part, okay, this part is somewhat simpler because of this following theorem. Okay, so theorem. First of all, I would say this is a lemma. Okay, maybe I am using pi. Let me continue with pi. If a problem pi 1 reduces in polynomial time to a problem pi 2, and pi 2 in turn reduces in polynomial time to pi 3, then the combination of these reduction algorithms is a reduction algorithm from pi 1 to pi 3. Obvious, right? I am not writing formally any proof for this. This is more a lemma rather than a theorem, but anyway, because of its importance, I wrote it as a theorem. If this follows from the definition and this lemma, pi 1 is less than equal to pi 2, and pi 1 is NP-complete, then pi 2 is also NP-complete. Right. Again, I am not furnishing any proof because it seems obvious. From every problem pi to pi 1 there is a polytime reduction, and from pi 1 to pi 2 there is a polytime reduction. Therefore, by this lemma, from every problem pi prime in NP there is a polynomial time reduction to pi 2. So, pi 2 is also NP-complete. Okay, I am not writing this formally. I think this is quite obvious. Okay. So, point is that to start with, we need some generic reductions. And once we have 1, 2 or 3 such problems, from those problems we will make reduction to some other problems. Okay. To prove that these new problems are again NP-complete. So, the first generic reduction was proposed by Stephen Cook and Leonid Levin independently in 1971, and that is called the Cook-Levin theorem. So, they proved these problems called SAT and CNFSAT. I will describe this problem soon as NP-complete by proposing a generic reduction from an arbitrary problem. After, we will not prove these things. This is most suited to your theory of computation course, and if you are interested, I will give you a pointer what to look at. From this, we will do something like this. We will prove some other problems as NP-complete, like Ham path or Ham cycle. They are all equivalent. Vertex cover. Delete this. Vertex cover problem. Maybe the click problem. And again, from this Ham path, we will prove the traveling salesperson problem, longest path problem, etc. in graphs to be NP-complete. From click, we will see independent set. Okay, so this way, so these are our first generation stars. Using those as first examples of NP-completeness, we make these second generation stars. Okay, and then again, assuming that these second generation stars are NP-complete, we will consider this third generation stars, and then fourth generation, fifth generation, sixth generation. This way, people have identified thousands of problems as NP-complete. Okay. So, what is SAT and what is CNFSAT? Let us see this. Okay. SAT stands for satisfiability of Boolean formulas. Okay. So, I know that you already know this Boolean formulas. So, let's say x1, x2, xn be Boolean variables. That is, they take only two values, 0 and 1, yes or no or yes, false or true, whatever you call. And the formula Boolean formula written like this. This evaluates true, evaluates to either true or false, 0, 1 or 0, whatever, for each truth assignment of the input variables x1, x2, xn. Okay. So we know that we can write any Boolean formula using these three primitives. Okay. So we often use this symbol and, or simply we write it as products. Okay. This is also called conjunction. And second primitive is or, which you often write at this or simply as sum. This is called a disjunction. And not. This is often written like not, or even by a bar or dash and prime, something like that. This is negation. You all know. Okay. And so you know, you are already, I would say, familiar with Boolean formulas. And one particular type, the CNF formula, I will now explain. Okay. So CNF is the conjunctive normal form. This is nothing but a product of some expression, Boolean expression. The sum of product form is called disjunctive normal form, DNF, and the CNF is product of some expression. So it's something like this. Okay, the sum of is a product of some expressions. Now I introduce a few, or I can write it like this. This. Okay. So I will use both this notation interchangeably. Either this popular class product form with bars or using this wages and V's. Okay. Anyway. Okay. So each sum in this product consists of, okay, let me formally mention it. So, okay, so you have the variables x1, x2 and so on, xn maybe. A literal is either a variable xi or its complement. A clause is an OR of literals. And a Boolean formula in CNF form is a AND of. clauses. Okay. So x1, x2 bar, x4, x3, these are all literals. x1 plus x2 bar plus x4 is a clause, x3 is a clause, x4 bar is a clause, x6 is a clause, x2 plus x3 bar plus x5, this is a clause. And this formula, which is a product of, that is an AND of these individual clauses, is a Boolean formula in the conjunctive normal form or the product of sum form. Okay. Okay. Just one more definition. Let phi be a CNF formula. Okay. If every clause contains exactly k literals, phi is said to be in the k CNF, k conjunctive normal form, in the k conjunctive normal form, where k is a constant. Positive integer. Okay. So now, for example, this is a 3 literal clause, 1 literal clause, 3 literal, 1 literal, 1 literal. So this is not in some KCNF. But if I have a formula like this, this is a 3CNF formula. Because each clause contains exactly 3 literals. Okay. Okay. So having seen these examples and definitions, I introduce these computational problems. Okay. I think I have some time to complete this. SAT. Okay. Before doing that, let me just introduce just one more definition. A Boolean formula phi in any form is called satisfiable if it evaluates to true or 1 for at least one truth assignment of the variables, input variables. And it is called unsatisfiable if phi evaluates to false for all truth assignments of the variables. Fine. Makes sense. So I'm not giving you examples like this. Okay, maybe I will give you an example. Consider this formula. X1 or X2 or X3 bar and X1 or X4, let's say. Is this satisfiable? Yes, for example, I can take X2, X1 equal to anything, maybe 1, X2 equal to 0, X3 equal to 0, X4 equal to 1. For this truth assignment, this evaluates to true because X1 is 1 and this is true because X4 is 1. So this is 1, this is 1 and 1 is 1. Okay. Whereas if I consider this, so this is satisfiable. Okay, on the other hand, if I consider this, X1 or X2 complement and X1 complement and X2, this is not satisfiable. Because if you want this to be satisfiable, this should be 1, this should be 1 and this should be 1. This should be 1 means X1 should be 0, this should be 1 means X2 should be 1, but then this is 0, 1 complement is 0, 0 plus 0 is 0. So this is not satisfiable. Okay, so now I define our computational problem, SAT. Given a Boolean formula, decide whether the formula is satisfiable or not. CNFSAT, same thing, except that given a Boolean formula, in the conjunctive normal form, decide whether the formula is satisfiable. And CNFSAT, same thing, given Boolean formula in the K conjunctive normal form, decide whether the formula is satisfiable. Okay. So if these formulas are satisfiable, a certificate for this is a satisfying truth assignments of the input variables. Okay. So if satisfiable, a satisfying truth assignment of the input variables is a certificate. Whereas, if the formula is not satisfiable, there is no certificate, no such certificate. Okay. So clearly, each of these three problems, SAT, CNFSAT and CNFSAT, is in NP. Okay. Because they have certificates, succinct certificates. Now, what Cook and Levin prove, this is called the Cook-Levin theorem. Okay. SAT is NP hard and therefore NP complete too. And their construction gives actually a corollary. Not exactly a corollary, a slight modification of this construction shows that. Okay, maybe I use again this. CNFSAT is again NP hard or NP complete. What about CNFSAT? I will come to that later. Okay. I will come to that later. Let us not worry too much about that. But these are the theorems that I will not prove in this course. So if you are interested, you may, for example, look at this book. I think the name is Theory of Computation. Okay. Or later, if I have time, I can give you a note which is based on a proof using non-deterministic polynomial time Turing machines. Okay. So, with the very important results from the Cook-Levin theorem and an associated result, we have now two NP-complete problems in our bag. These are our first generation stars. Then from the next session onward, I will start generating second and third generation stars. Okay. By reduction from SAT or CNFSAT. Usually we will use CNFSAT because this is more structured. Formula is much more structured. So I will. So of course these proofs are difficult because these are generic proofs. But some of the proofs that we will do for generating our second generation stars, these are also quite involved and counterintuitive, but anyway people came up with those nice ideas. So some of this I will share with you. Okay, so I am approaching 1 hour for today, so let me stop. Is it so? Yes, yeah. Okay. So see you.